Today we're taking on a really cool one. We've gotten some messages from you all about the behavior of electrons in atoms, and specifically whether electrons in the same orbital could be entangled. Now, quantum mechanics is notorious for being a bit mind-bending, but I think by the end of this deep dive, you'll have a much clearer grasp of what's going on. So let's jump right in.
Yeah, this is definitely one of those topics that can really trip people up. The line between classical correlation and true quantum entanglement can get pretty blurry.
Okay, so maybe that's a good place to start. Could you walk us through what entanglement actually is and what makes it so different from just regular old correlation?
Entanglement, it's a bit more than just a connection. It's like these particles have their fates intertwined at a really fundamental level. Let's say you have two entangled particles, and then you measure a property of one of them, like its spin. At that very moment, you instantly know the corresponding property of the other particle, no matter how far apart they are.
Whoa, okay, faster than light. That's wild.
It really is. It's this instantaneous correlation that makes entanglement so mind-boggling. And I remember some of the listener questions mentioned superposition, too.
Oh yeah, superposition. That's another one of those quantum mechanics concepts that can feel kind of impossible. Can you give us a refresher?
Think of it like flipping a coin. Classically, it lands on either heads or tails, right?
Right.
But with superposition, it's like the coin is both heads and tails at the same time until you actually look at it. Entanglement takes this a step further. Those particles are in this fuzzy, undefined state until we measure one of them, and then it's like that act of measuring forces the other one into a definite state, even if they're miles apart.
Okay, so I'm starting to see how entanglement is this weird non-local connection. But how does this apply to electrons whizzing around an atom?
Yeah, that's where things get interesting. We need to think about orbitals. You've probably seen those diagrams of the different orbital shapes, AS orbitals, P orbitals, and so on.
Definitely. From chemistry class, they weren't always easy to visualize, though.
They're not meant to be actual paths that electrons follow. It's more like regions of space where you're most likely to find an electron, and each orbital can hold a maximum of 2 electrons.
Right, and one of the questions we got mentioned that if you know the spin of one electron in an orbital, you automatically know the spin of the other one. That sounds a lot like entanglement.
It does, doesn't it? And that's a really insightful observation. It gets to the heart of why people get confused. It's true that the spins of those 2 electrons are correlated, but it's not because of entanglement. It's because of something called the Pauli Exclusion Principle.
Ah, yes, the Pauli Exclusion Principle. I've definitely heard of that, but a quick refresher would be great.
Okay, so basically it's this rule that says no 2 electrons in an atom can be in the exact same quantum state. They can't have all the same quantum numbers, which describe their energy, their orbital, and their spin.
So like 2 runners in the same lane can't be in the same position at the same time.
That's a great analogy. Since electrons in the same orbital already have the same energy level and orbital shape, the only thing left that can be different is their spin.
So one spin up and one spin down, like a cosmic dance routine.
Haha, exactly. It's like this built-in rule preventing them from being total clones.
Okay, so knowing the spin of one tells us the spin of the other, but not because of spooky action. It's just because they have to be different to follow the rules of the game.
Right. It's like a cosmic choreographer making sure everything stays balanced. And this is where it gets important. Their spins are already decided before we even try to measure them.
So we're not collapsing any superposition or anything. We're just peeking in and seeing how they're already arranged.
Precisely. Think of it like having 2 coins and one's always heads and the other's always tails. Even before you look, if one is heads, the other must be tails. No mystery or weirdness about their states.
Gotcha. Just a simple correlation, not quantum entanglement. But I'm looking at another excerpt here that says, aren't they in a superposition because you don't know which one is which until you measure? I could see how that would be confusing.
Oh yeah, that's a common misconception. It's important to remember that thanks to the Pauli Exclusion Principle, their spins are already set before we measure anything. It's not like Schrödinger's cat where the act of opening the box changes things.
Right. That cat is actually in a superposition until we look.
Exactly. But with electrons in an orbital, their states are already decided. We're not uncovering some hidden truth. We're just revealing the arrangement that was already there.
Okay, so it's not like they're both spin up and spin down at the same time. They each have a definite spin. We just don't know which one is which until we look.
Exactly. And when we do measure one, it's not changing anything. It's just telling us what the other one must be because of that predetermined choreography.
Okay, I'm with you so far. But one question that came up a lot was about the evidence for this. One listener even asked, what's the definitive evidence they're not entangled? That's a tough one to answer. How do scientists approach that?
It's a really good question. It is hard to prove a negative, but we do have multiple pieces of evidence that all point in the same direction. First off, the standard model of particle physics, which has been incredibly successful in explaining the universe, doesn't have any way to explain entanglement within an orbital.
And then there's the wave function, right? That mathematical description of the electron state.
Right, and the wave function for two electron in an orbital isn't a jumbled mess of entangled states. It's a very specific and well-defined state described by what we call a Slater determinant. It's basically enforcing the Pauli exclusion principle mathematically.
So it's like the wave function itself is saying, nope, no entanglement here. These electrons are following the rules.
Haha, exactly. And on top of all of that, we've never ever seen any experimental evidence of entanglement within a single atom. If it were happening, we should see some pretty strange and noticeable effect. But we don't.
So while we can't rule out some wild new discovery in the future, it sounds like the evidence we have right now is saying those electrons aren't entangled.
It seems that way. It would take some extraordinary evidence to overturn all of that. We'd be talking about a huge shift in our understanding of quantum mechanics, or maybe even the discovery of some entirely new forces or phenomena.
Okay, well, that's a little reassuring in the universe is still incredibly weird, but at least it's predictable kind of way. But speaking of weirdness, before we move on, I have to ask, what if we just for fun imagined a world where those electrons were entangled within an orbital? What kind of crazy possibilities would that open up?
Ooh, I love a good what if. Let's take a little speculative side trip after a quick break and explore some truly mind-bending possibilities.
All right, so we've established that based on what we know now, electrons in the same orbital aren't entangled. But where's the fun in stopping there? What if we let our imaginations run wild for a bit?
I'm always up for a good what if. It's those out there questions that often lead to the most exciting discoveries.
Exactly. So just for argument's sake, let's say we somehow found undeniable proof that electrons within the same orbital are entangled. What would have to change in our understanding of physics for that to even be possible?
Well, one possibility is that the Pauli exclusion principle, that rule we've been talking about, might not be as ironclad as we thought.
Okay, so you're saying there might be some wiggle room in those quantum rules?
Maybe. Perhaps under extreme conditions, like the crazy densities you'd find at the heart of a neutron star, or the first moments after the Big Bang, those rules we take for granted might start to break down.
Okay, that's definitely extreme. So in those situations, those two electrons in the same orbital could in theory have the same spin.
It's a wild idea, but not entirely impossible. Instead of that rigid anti-correlation we normally see, maybe we'd start to see a partial correlation that's best described by an entangled state. Imagine a superposition of up, down, and down, up with a tiny bit of up, up, and down, down thrown in.
Now that would really shake things up. Could this hypothetical entanglement even play a role in those big cosmic mysteries like dark matter and dark energy?
It's a fascinating question, and one that physicists are definitely thinking about. If the Pauli exclusion principle isn't as absolute as we thought, it could have huge implications for the large-scale structure of the universe.
So bending or breaking the Pauli exclusion principle is one way to open the door to entanglement within orbitals. What other radical shifts in our understanding could lead us down that path?
Well, another possibility is that there's a whole new force of nature that we haven't discovered yet, something totally different from gravity, electromagnetism, and the strong and weak nuclear forces.
The hidden force. Okay, now we're talking. What would make this new force so special?
Imagine a force that's non-local, meaning it can act instantly across space. That could be the key to connecting those two electrons in an orbital, even though they're so close together.
So even though they're practically on top of each other, this force could entangle them.
Exactly. It's like an invisible thread tying their destinies together.
Okay, that's pretty mind-blowing. What kind of impact would a new force have on our understanding of atoms?
It would be revolutionary. We'd have to completely rethink everything. It would be like finding a secret room in a house you thought you knew inside and out.
And just think about the technology. Could we harness this entanglement for things like quantum computing or communication?
It's definitely possible. If we could figure out how to control this new force, it could unlock a whole new world of technological advancements.
Okay, so we've got a modified Pauli exclusion principle, a brand new force of nature. Are there any other equally crazy scenarios that could lead to entanglement within atoms?
Oh, there are a few more. And they get even weirder. How about the possibility of quantum gravity showing up at the atomic scale?
Quantum gravity, now we're talking about the big leagues, trying to merge quantum mechanics and general relativity. But I thought quantum gravity only mattered at super tiny scales way smaller than an atom.
That's what we used to think. But what if we're wrong? What if all those super precise atomic clocks we're building, or those sensitive interferometers we use to detect gravitational waves, start showing us tiny hints of quantum gravity messing with things inside atoms.
Oh, yeah, I see where you're going with this. So you're saying those quantum gravity effects could be what's causing the entanglement between the electrons.
Exactly. Maybe the fabric of space-time at that tiny scale is fluctuating in a way that entangles those
So
electrons.
it's like those electrons are getting a taste of those mind-bending effects we usually associate with black holes and the Big Bang.
Precisely. It would change everything about how we view space-time and matter.
All right, trying to keep up here. So far, we've got extreme conditions altering the Pauli Exclusion Principle, a brand new fundamental force, and quantum gravity playing tricks on us. Is there anything else we can throw into this mix?
Well, we could add another layer of weirdness with extra spatial dimensions maybe influencing those electron interactions.
Extra dimensions. All right, you're really taking us down the rabbit hole now. I thought those were just theoretical ideas from string theory.
They are. But what if they turned out to have real observable effects? What if those extra dimensions all curled up at tiny scales were subtly influencing the behavior of particles within an atom?
Okay, I'm trying to wrap my head around this. So you're saying those hidden dimensions could be like a secret passageway for those electrons, allowing them to communicate and entangle in ways we can't directly see.
I like that analogy. Maybe those electrons are actually closer together in those extra dimensions, creating a shortcut for entanglement.
My head is spinning. But I'm noticing a pattern here. All these scenarios require a pretty radical departure from what we currently understand about the universe.
You got it. Whether it's tweaking the Pauli exclusion principle, adding a whole new force, throwing quantum gravity into the mix, or even messing with extra dimensions, we'd need to rethink some pretty fundamental physics to make room for entanglement within an orbital.
It sounds like a revolution in physics is in order.
It would be, but that's what makes science so fun. It's always changing and evolving. Who knows what mind-blowing discoveries are waiting for us just around the corner.
Okay, well, after that whirlwind tour of hypothetical universes, I think it's time to bring us back down to Earth for a bit. Can you help us sum up what we've learned? What are the key takeaways you want our listeners to remember? Okay, so after that wild ride through hypothetical universes, I think I need to get my feet back on solid ground.
Haha, yeah, it's always good to come back to reality after exploring those what-ifs.
So let's recap for our listeners. We started with this question of whether two electrons sharing the same orbital could be entangled.
Right, and it turns out it all comes down to the Pauli exclusion principle.
Yeah, could you remind us one more time how that works?
So the Pauli exclusion principle basically says that no two electrons in an atom can have the same set of quantum numbers. They can't be identical in terms of their energy, their orbital, and their spin.
And since those two electrons are already sharing the same orbital and energy level?
The only thing left that can be different is they spin. One has to be spin up and the other spin down. It's like they're programmed to avoid being total twins.
Right, so knowing the spin of one tells you the spin of the other, but not because of some spooky action at a distance.
It's all thanks to the Pauli exclusion principle. They're correlated but not entangled, and their spins are already decided even before we try to measure them.
We're just peeking in to see how they're already arranged, not causing some kind of collapse of a superposition.
You got it. It's like those two coins where one is always heads and one is always tails, no mystery or uncertainty about their states.
So simple correlation, not quantum entanglement. And we talked about the evidence for this. The standard model of particle physics doesn't include any way to explain entanglement within an orbital.
And we've never seen any experimental evidence of it either. If it were happening, we should see some pretty weird effects that we just don't observe.
Right, and those hypothetical scenarios we discussed all require some pretty major changes to our understanding of physics.
We'd have to modify the Pauli exclusion principle, or discover a whole new force of nature, or even find evidence of quantum gravity acting at the atomic scale.
Or maybe even those extra dimensions from string theory. It's fun to think about those possibilities.
It is, but for now it seems like those electrons are sticking to their classically correlated dance moves. No entanglement for them.
But even though those electrons might not be entangled, they've certainly entangled our minds today.
Well, hopefully in a good way. It's important to keep asking questions and exploring these topics.
Absolute. So for our listeners out there, keep those minds curious and keep exploring the wonders of the quantum world. Who knows what amazing discoveries are waiting for us out there. And that's a wrap for this deep dive. Thanks for joining us.